Hi, everybody. Welcome to Data Platform Summit. My name is Hasan Savran, and I am here to speak about graph database tables in SQL Server. I will cover graph database tables, how to create them, how to create indexes on them, how to retrieve data from them. There are a couple of new features in SQL Server 2019. I will cover them with you. And we will end the session with a couple of demos. So I hope everybody's going to learn something new. Let me talk about myself too before we go in the presentation. As I said before, my name is Hasan Savran, and I am a Microsoft Data Platform MVP from United States. I am located at Cleveland, and currently I am a business intelligence manager at one of the big companies, insurance companies here. I have been doing web development for 15 years, and almost 7-8 years I'm in a business intelligence team. I am very active online. You can follow me if you like on the LinkedIn or Twitter. And I'm pretty active. I share whatever I know, really, mostly SQL Server, Cosmos DB, C# in my blog. I try to write at least once a week. And if you will have any questions about this session, please follow me and ask me any questions from any of those platforms. I will be happy to answer them for you. All right, now let's jump in our presentation. Graph database tables. What are they? Graph database tables are introduced to SQL Server in 2017. Before 2017, though, graph database tables will still exist in other products. So they are not really new technology. They have been out there for a long time. So what are they? Well, to understand what they are, we try to understand first, like what type of problem they are trying to fix. We live in a connected world, and in this connected world, things changes quickly. When I say things, usually in our case, businesses changes quickly. For example, look at the evolution in the entertainment, right? We used to have all kind of companies which was renting videos. All of them disappeared, and new companies came up, and things are continue changing. Look at the evolution in the cars. They are getting smarter and smarter. Well, that's affecting insurance industry, or the way that you sell the car is changing. Look at the evolution in IoT. IoT devices are everywhere right now, and we are getting all kind of information from those IoT devices, and we need to kind of connect that data and analyze the data. Also, evolution in healthcare. Everything used to be on paper. Now everything's on electronic charts, and those changes are not easy changes, and those are big changes. When those changes happens, what happens? Our data changes. Creating data models in relational databases can be a challenge, and it's getting actually more difficult because of those things that I have been counting, because the data is changing, because everything else is changing around us. Your business might be selling, product X today, and one day you will go to, your job, and they say that, what, we are selling product Y now. When a change happens like that, what happens actually in your end is your data changes. Because of these big changes in business, your data is gonna change, and you might need to introduce new domains or new relations to your data model. It sounds easy, which can be really challenging in relational databases. Because usually relational databases do not really like changes. It's much easier to create the relational data model when actually they give you the problem, when it's in front of you. You can create all the relations, everything will work perfectly. But you really have to be think about feature when you are creating the data models. It needs to be flexible. It needs to evolve with your business. So whenever you are trying to create a data model, you really need to think about not today, but tomorrow. What might change? how I can make this more flexible so it will be easier to create, join more tables here. And that's not an easy case. Also, relational databases have some other limited options. For example, you cannot create many-to-many relations between two tables. You need to create another table, and that's going to create, keep your primary keys and foreign keys. Usually they call it junction table, which makes you create the many-to-many relation. But the problem is it causes two more joins, right? Both tables have to join to that junction table. Usually joins means, well, slowdowns. For example, look at this picture. I picked this picture actually to explain how the, relational database works. If you think about each highway is a table, well, you need to do joins. And when you need to join, if you are going in one of those highways, let's say 100 kilometers, when the junction comes up, well, you're going to brake. You're going to slow down. Depending how bad that curve is, you might really need to slow down. And that's exactly happening in relational databases. So graph database tables has some, answers for the things that I just count here. And we are going to look at some of those problems, answers, and I'm going to try to show you how graph database tables actually, try to fix those problems. Now, second question I want to answer here is, who is using them? Now, the first one I can give you is the suggestion engines. Now, you might say, what the heck is a suggestion engine? Well, the best example I can give you is, let's say, we are learning something here, right? So let's say Kubernetes is everywhere, right? And we say, well, you know what? We really need to learn Kubernetes. And I'm going to go to Amazon and I'm going to look at some of the books. So you look at some of the books and you pick one pretty good one, right? And you click on it, you look at the product page, there's a picture of it in the right side, price, you kind of go down, their description, maybe more like reviews, and you like it so far. Then you scroll down more and you start to see really interesting things from Amazon. It starts to suggest you stuff like this one. It says, well, if many people who's buying this product also buying this product, that's a very, very interesting thing. If you try to think how to do this with relational database, I don't think you can even do this dynamically in relational database. The best option I can really say, maybe you can create an SSIS package, which will run maybe once a day or, I don't know, really every 4 hours, and look at all the data and put this kind of suggestions in a table. So whenever user goes to this Kubernetes page, rather than creating this all kind of joins that I don't know how many joins we are going to need to actually make a suggestion like that dynamically, we will go and look at that table. That's a solution. As I say, my point is this is not easy to do in a relational database. So graph database tables gives us an option to solve this problem. Second one is government. I picked the government here because government has many agencies, right? So let's say you are a cop and you are investigating something and you have maybe ID of a person, right? You go to your computer, you type the ID and you click search. Now, you have many data points. Your government has a lot of agencies and probably that person has record in many of them. So when you click the search, the last thing you want is have the same data, like the person's name, age, date of birth, see multiple times, right? Because that's going to be the same data from both all agencies. So in other words, you want to have like a master data management database. Graph database tables are great for master data management systems. Third one is social media. Social media has been using graph database tables for a long time. The best one I can give, the best example I can give you is probably Facebook. So if you think about Facebook, what do? Usually? You log into Facebook, you look at all the posts, and really, mostly you just click the like button, right? So if you try to think alike, technically what's really happening is you are the user, you are the entity, and you have another entity out there. It can be a picture, it can be a shop, it can be a post, it can be anything that Facebook has. And the relation is going to be same, like. In relational database tables, does not even exist. You have primary key, you have foreign key, that is your relation. You cannot create this relation in different entities like that. In graph database tables, you can do that. Also, graph database tables are great for hierarchical data. And hierarchical data, we have some options in SQL Server for hierarchical data. Hierarchy ID is a great option if you are looking for a hierarchical data solution. It has been out there since 2008, and you really don't need this latest version of SQL Server to use it. But it's for really highly structured data. In other words, if I try to explain that, think about your HR, right? So you have a CEO on top, and it goes down from there. And CEO can have many managers under that. Each manager can have many supervisors, and each supervisors can have many employees. In graph database tables, we do not have a fixed boundaries like that. For example, you can have a manager who might have multiple reporting to multiple managers. You might have multiple CEOs. In hierarchy ID, that's not the case. In hierarchy ID, multiple parents are not allowed. And you can have only one root, as I said before. You can have only one CEO. You cannot have multiple CEOs. If you have multiple CEOs, that means you need two tables. They cannot go in the same table. And graph database tables are very flexible, and they really don't care. You can create a one-to-many or many-to-one or many-to-many relations with graph database tables. To find the data, if you are using hierarchy ID, you need to use the CLR function, since hierarchy ID is a CLR data type. And it's indexable. You can index the hierarchy ID. In graph database tables, same. The things you need to know about the graph database tables, it has been out there. It's newer, SQL Server 2017 or later, you're going to need. And you need to use the match clause to find the data you are looking for, which I will cover in this session in a little bit. All right, next, let's try to see how actually this is happening in graph database tables. In graph database tables, the first thing you need to know is relationships are first-class citizen in graph tables. That means relations has their own tables. We have two types of tables in graph database tables. First one is node tables. Node tables keeps entity data. What is entity? Entity can be users. Entity can be products, orders, cars. All of those are entities. And each node tables has a special column named node ID. And that's the identity of the entity that you create. And that is actually getting populated itself. You have absolutely no business with it. You cannot change it. You cannot delete it. And every time you insert data, there will be a node ID for that entity. But the system uses the node ID to find data in the backend. So you might not use it, but it's good to know it's there. And it's indexable. Whenever you create a actually node table, if you don't create an index on node ID, system actually creates it for you. Node tables can have any type of data types. So if SQL Server supports the data type, you can put in the node table. Edge tables, well, that's the things get a little bit interesting. Edge tables keeps the relations between entities. Just like the node tables, we have an identity column named Edge ID. Edge ID is the identity of each relation. Just like node ID, you cannot change them, you cannot delete them. It's always going to be there. It's always going to be populated. You can create any type of data types in HTables. That is very interesting. That means you can create all kind of metadata for your relations that you create. That doesn't exist in regular relational database tables. Everything has to go into one table, and you might end up with a lot of columns. In HTables, it's not like that. We have two more special columns in HTables. Those are from ID and to ID. That's actually how you create relation between two entities. Relations cannot be updated. You have to drop the relation and insert it again if you like. So you cannot update from ID and to ID. You can update the other columns that you create. Those metadata, other stuff, you can update them if you like. And directions are important. What does that mean? So to actually explain that, let's give you an example. Let's say we have users table and we have a bunch of users. And we have a relation table named, let's say, like. So what we want to do is we want to get two users and make a relation between them. So we are going to say one user likes the other one. So let's say we have a user 1 named Alec. We have a user 2 named Anna. Now we want to say Alec likes Anna. To do that, first we are going to go and get Alec's node ID from the node table and put that in the from ID. Then we are going to get the Anna's node ID. We're going to put that in the to ID. That's going to make a relation between Alec and Anna. And whenever we search who likes who, then we are going to find that Alec likes Anna. That's where directions are important comes up. When I say directions are important, what I really mean is, in our case, Alec likes Anna. That does not mean Anna likes Alec back. If you want to make that relation again, then you need to create another row out there which says Anna likes Alec. That's why the directions are important. All right, so next slide here. This is actually how you create the node tables and edge tables. As you can see in this example, we are still using the create table syntax. We are putting all kind of columns that we want to put in. And as you can see, we don't even define the node ID or anything like that because everything is getting created automatically in the backend. So really the only difference here is the as node. As you can see, this is it. That's all syntax you need to know to make a table node table. Just the edge tables relations, they are same. As I said before, you can create metadata in edge tables. That means, for example, in here, I want to track when I create this relation. So I'm just looking the created date. And just by making it as edge, I am making this table a relation table. So that's the only difference between these two, really. And as you can see here, I am not defining edge ID, I am not defining from ID, I am not defining to ID. Whenever you say as edge, all those are going to be actually created automatically in the backend. So when we create these tables, if you want to see them where actually they get located, you can find them under the graph tables folder. And as you can see, I have a bunch of tables out there, and the tables that I just created are products and alike product. There's like a special kind of icon out there. I don't know if you can see it. Almost looks like a glasses for relations table, and just like a one dot for node tables. So that's where you can find them. Now we know how to create the tables. Let's talk about how to insert data. To insert data, we are going to use actually either insert statement, just like regular. just like you insert in a regular table, you just need to pass the which columns you want to insert data into and your data. So really the node tables, there's absolutely nothing different when it comes to the inserting data. Edge tables is a little bit different. So in edge tables, in our case, we created this column named credit date. So we had to pass, we really don't need to because we create a default constraint out there. So if we don't pass it, it's going to get the current date, but I just put it out there as an example. So in a like product table we are creating, and just like the user example I gave you, Alec likes Anna, in this case what I'm actually doing here is I am getting the product ID once, node ID, and I'm putting that in the from ID. That is the first one here, as you can see, and my to ID is gonna be the second product, which is the 2. I'm guessing it's gonna be Kindle Fire HD8. So what I'm really doing here is I am creating a relation between 2 products, and I'm saying this product is like that product. That's all I'm doing here. All I have to do is get their node IDs and put them in the right order to the relation table. Now, don't forget, you cannot update relations. Don't forget that. All right. So when it comes to the update, other thing you can know is, well, when it comes to updating the node tables, it's just the same update syntax. You just need to pass which table and what you're updating. In the edge tables, as I said before, you cannot update the relations, but you can update anything else. For example, in this case, I am updating the L-like product, and I'm saying I'm just changing actually my credit date. That's the metadata I created in this table, and I'm just changing it. So don't worry about this one. I'm going to cover that in a little bit, but that's how you actually update the relation tables. All right, so now we create the tables. We know how to insert the data into our tables. We know how to update it. Now, let's actually select some data. You can actually go and just write select all from node table or edge table. So whenever you do that, you are going to actually see the node IDs. For example, those are the node IDs and the edge IDs. This is my from ID and this is my to ID. Now, as you can see, all of those are in JSON document and system uses them. So probably you are going to have absolutely no business with them. But it's good to know that if you're going to write select all from those tables, you will see those columns and they will be there. All right. Now, if you want to actually find the data in graph database tables, you are still going to use the select statement, but you need to use a new syntax in your where clause, which is match. Match takes graph search pattern, and graph search pattern specifies the pattern to search really in the graph database tables. The pattern needs to go from one entity to other entity by using a relation, and that's the minimum requirement. You can have multiple if you like. And well, whenever you are going to actually use the graph database tables, you are still going to use a couple of tables. So it's probably you're going to use aliases rather than using the name of the table. So we are going to use the parentheses to remark the relation tables because it's going to be much easier to kind of read it like that. Also, as I said before, the direction is important. So in that case, what we are going to do here is we are going to use arrow character to specify which direction we are writing this query for. Here's an example, a simple example. What I'm doing here is I am using my products table, wish table, and users table. As you might guess, my products table is an entity table. My users table is an entity table, and wished is a relation table. And my match clause, as you can see here, is going from users to products table by using the wished relation. and I only care about the user ID 1. So that what is this going to actually do is it's going to give user ID 1's wish list by just running that. So let's try to give you a little bit more examples how to use this match. My first example for you was the Amazon. When you go to product, it gives you alike products. So here's an example. So we go to a product page. We are looking Kindle Fire from Amazon, and I want to show my other products like Kindle Fire. So here's going to be our case. My user is going to go here, and I'm going to show my user the other products I'm going to have. As you can guess, my product is the node table, and I am going to have a relation table named alike. And I'm going to do that at the back end first to be able to use it. So if I want to show my user alike product of any product, then my query is going to be like this. So you're going to pick whatever columns you want to display. Then I'm going to use my products table. I'm going to use my alike relation table. My match is going to go from my product table to product table by using the alike relation. And in this case, let's say the ID 1 represents the Kindle Fire. This is going to actually give me all the products I have, which is like Kindle Fire in my system. So it's dynamically, I can actually run this query very easily and be able to return the list dynamically. Next example, healthcare. And this is a very common problem in healthcare. So let's explain. So let's say we work in a hospital, and well, our patients, come to hospital, but they can really go in many other doctors or many other, the areas that take the patients. And usually when they go to other doctor offices, they might give them a different medical record number. They can send them to a lab. When they go to lab, they are going to have like lab number. But there's going to be some, common information with those patients. Right? The name is going to probably match. Hopefully they're going to have an ID, like in the United States, we have social security number. I'm not sure what other you have in your countries, but I'm sure everybody has a number that identifies them. So you kind of give that to your doctor, to your nurse, to your, the lab person. So you go all of those different places. And whenever you go to the hospital for anything, your doctor wants to see, the history of your maybe lab, your doctor visits and other stuff. So if you have a system which actually gets all this data from different kind of offices to one place, what's going to actually happen here is, if we are talking about, for in this case, let's say our patient is Michael Miller, he's going to have many records coming from many places. And when the doctor opens that, he doesn't want to see all those things again, again and again, the same information. He wants to see, this is the Michael Miller, those are the records we have. And that's it. We're going to give a summary. To do that, though, this sounds easy, but it's a challenging project, because you kind of need to go and find Michael Miller's all records in the back end, and you try to match them and merge them if you believe that those records are the same people's. In some cases, you might have, differences. Maybe one doctor calls him Mike Miller, other doctor calls Michael T. Miller, right? So you need to have some rules. And in graph database tables, you can do that very easily. So we have patient, and we have the relation named same. So you need to kind of work on that same relation, because you don't want to just give that to you want to be sure that this is the same people before you create that. So that's going to be a business logic that you need to run in the backend. But as soon as you know that this is the same person, you can create this relation dynamically in graph database tables, and everything will be available immediately in your web application. So if you actually look at that in here, we are going one patient to other patient, and let's say this is the Mike Miller ID 1, and this is going to give you all the Mike Millers that you have. from any systems you might be connected. Next one, we talk about the social media. So this is a picture from the social media, I think from Facebook. As I said before, what do you do usually? You just click the like button, right? Which is right here. So when you click this like button, what's going to really happen here is you are the user. And you might be able to like a post. You might be able to like a photo. You might be able to like any entities. So what's really going to happen is when you click the like button, you are going to create a relation between you and an entity, which is named like. So if you want to see actually all the whatever, I like or a user like, that's going to be very easy. You are going to go to users table, and let's say in this case we are looking on the posts. So I'm going to find all the posts liked by this user. We are going to use the ID one. So let's say, I don't know, this is me, and this is going to give me all the posts that I like in the Facebook. It's pretty easy. Now, as I said before, there are some new features came up in SQL Server 2019. So now the ones that I'm going to actually show you is going to be available only in 2019 and Azure SQL. Now, the first, let's explain the problem. In 2017, everything came and, people were excited, but there are some problems. For example, let's look at this model here. We have a user, we have a product, and maybe we have a relation between them is wish. So this is going to give you the wish list of user. In 2017, nothing is stopping you to make relation from user to product. Also, nothing is stopping you to make the same relation from product to user. Doesn't make sense. Product likes the user or product wishes user. Doesn't sound good. Doesn't sound right. And the problem is in 2017 you can do that. In 2019, Microsoft actually came up with a solution, and you can now actually create constraints between the node tables. So you can actually define which relation can go from what product, what entity to what entity. So let's see an example here. This is the most simple one, and as you can see, I'm still using the alter table syntax, and I'm giving a name for it, and I am actually altering a relation table here, which is a wished, and I'm saying my connection can go from users to product table. You are actually defining where this relationship can be coming from and can go to. This can get a little bit more complex, so it's very simple here. If you want, you can actually define here multiple locations. So in here, for example, I'm saying my connection can go from users to product, or it can go from guests to product. We can do that. Other thing what we can do here is, that's another problem you might have in 2017. What happens actually if a user is deleted, but that user actually has maybe some relations between other users or other entities you have? What do you do in that case? In 2019, it gives you an option. So if you want, for example, if you are going to delete a user and that user actually wish many products, well, if you are going to say on delete cascade at the end of the constraint, SQL Server will delete all the cascade relations. So when you delete user 1, you will lose all the relations here. Yes. Or if you don't want to do that, you can just let SQL Server to throw an error whenever they try to delete a user, which if the user has an relation, then SQL Server will throw an error rather than deleting everything. So those are great options, but as I said before, they are available in 2019 or Azure SQL. Next one. So what do we have so far? Let's give you a summary. We know what node tables are, what edge tables are. We know how to create them. We know how to update them. We know how to select data from them. Now, what about indexing? Indexing is important in graph database tables too. Now, you can index those tables by any metadata you created them. That's exactly the same. There is nothing different. If you want to, for example, we did create a date in the relation table, you can create any kind of index on that. It's just a regular column. What I'm going to focus here is those special columns that I have been talking about in graph database tables. As I said before, when you create a node ID, I mean the node table, that node ID in it will be get index, you like or not, because SQL Server will automatically index that if you don't create an index on it. So that one is fine. Edge tables is the one that you really need to watch. Now, we have Edge ID, From ID, and To ID. Microsoft recommends you strongly to create indexes on From ID and To ID in your Edge tables, because system is going to use those columns to find the data. So you might not put them in your select statements, but system is going to actually use them to find the data. So it's pretty important. To give you a demo, here is an example we have. So in this example, what we are looking here is we are finding alike products. As you can see, it's pretty simple. My match clause is going from product table to product table by using the alike product and giving the product ID 1. So this is really the same with the Kindle Fire example I gave you. Now, if I don't create an index on my alike product table, this is going to be my execution plan. Really, what is important here is this one here. It causes a table scan because, well, unfortunately, there's no index on my relation table. And SQL Server is going to go and try to find all the data in the relation table. And I end up with a table scan. To fix this problem, it's pretty easy. Just creating index in this table will actually get rid of this table scan. Here, I'm actually using the same create non-clustered index syntax. And I'm just giving a name for my index. And all I'm really doing here is I'm creating two indexes in my two relations table. And alike product is the one which I'm going to use here. I'm just passing the from ID and to ID. And that actually creates a unique non-clustered index on it. Now, after I'm done with this, I can actually go and run the same query that I just showed you. And guess what? Now I don't have a table scan anymore, and I'm hitting an index seek, and everything will work much faster in this way. The best thing about the graph database tables is really using the SQL Server, how it, nothing is really that much difference. You are still using the insert statement, update statement, delay statement, create index, alter table. All of those are, you already know them. So really, graph database tables just really using the SQL servers, all of its structures, all of its their features. They are not really adding a whole new, I guess, syntaxes and other stuff. The only thing that's really new here is the match clause here. Rather than that, the rest of them is really not that a big deal. All right, so other option we got in SQL Server 2019, it's a pretty big one, is shortest path. In really summary, all it does is it finds the shortest path between two entities. You are still using the match clause, and you put the shortest path in the match clause. The challenge with this one is it introduces many new syntaxes. So it's not really that simple. And look at here, for example. Whenever you are writing the shortest path, as I said before, you must use all of those syntaxes. So you need to actually use graph path aggregation functions. You cannot just here say select this column, that column. You cannot do that. Also the tables, you need to tag which tables we are going to actually use for the path, for the graph search. Also, you need to define the arbitrary length. That means, you might have table like millions, 10 millions, billions records in them. And whenever maybe you are looking the shortest path, you are looking only, I don't know, maybe 2 or 3 hops from this entity. You don't want to go and search the whole table. So you can actually define it here. When I see this first time, I was just like this. I was like, whoa, what is this? This is almost like a whole new language out there itself. It can be really confusing, and it took some time for me to understand it too. I'm not gonna, lie. But when you get it, you get it. It's a little bit different way to kind of think. So to explain that a little bit, let's actually look at what those syntaxes look like. So those are the options that you can have. For example, graph path aggregation functions. It has to be one of those functions you see in this list. And you are going to use the within order class. Order class is always going to be group graph path. When you go to the from tables, it can be node or edge tables, but you need to actually define which tables we are going to go and look for the shortest path. Usually, your first table you're going to hear is not going to be the one you're going to look for because that's where you are starting from. Usually, the rest of them is going to be, you need to tag them as for paths. And as you can say, we put the shortest path in the match class here, and we are going to put the graph search pattern in the shortest path. And also, we are going to have plus or 1n, which is going to actually tell you or tell the system how many hops it can go. Can be, if you put it plus, it can go until the table finishes. Or you can say that, you know what, I am looking users here and I really don't care after 3 hops. So you can say 1 to 3 and it will stop after the 3 if it cannot, find anything. So there are a lot to cover here, and I think it's much easier to understand really what's going on here if we jump in to demo and actually see this in action. So I am gonna actually jump here to my management studio. So let's do that. The first thing I am going to do here is let's go and look at what we are doing here. Now, I'm going to demo first the shortest path. So what I'm going to actually do here is I'm going to create table named people. That's going to be my entity table. As you can see, it's very simple. And I'm going to create a friend. That's going to be my relation table. And let's do that first. Let's see everything is working fine. Then I'm going to insert some data in my people table. Then I'm going to create some relations between people. And I'm going to make them friends. So in here, for example, I'm putting people 1, people 2, and I'm making them friends. So let's do that here and run all of this. Execute it. Now I have 6 relations, which is great. Now, as I said before, this is a 2019 function, not 2017. And in here, on purpose, I actually connected to 2017. So if you try to do this in 2017, guess what? SQL Server is not going to know what this is. So you need the SQL Server 2019 to actually run this. Now, if I'm going to actually go and let's run this one more time, and go and look at what this is going to actually create. As you can see, what I'm doing here is I can pick. I told you that you cannot really use the column names. You can use it as long as it's not tag as for pet. So in here, the person one is not, because that's the one that I'm starting from. I'm using the string aggregate function here, and I'm just putting this character between the people. And as I said before, this is the graph order is always going to be same, graph pet. So I'm calling this one friends, and you can use the last value. Last value is going to give you what is the last value in that hop that you are making. So rather than running the whole, I'm just going to run this inner query here for you, and let's look at the data. As you can see, I am starting with the looks like the person ID 1 is Bob, the George, and George knows Bob. George knows Bob. Bob knows Katie, and it goes all over here to the like 6 relations. Now, this gives me the whole, I guess, the structure, whole hierarchy. But I don't want the whole hierarchy. I want to see the shortest path between George, and I'm passing Lisa here. So if I actually run the whole query, this is going to give me what is the shortest path that George actually knows Lisa. And as you can see, we can reach this combination. George knows Bob, Bob knows Katie, Katie knows Mike, and Mike knows Lisa. So that is the shortest path that we can actually reach from George to Lisa. Now, to show you that how this one actually changes, I have 2 more actually relations here. What I'm going to do here is I'm going to actually make this path a little bit smaller. So let's actually run this. Let's run the whole thing. So what I did here is actually, if you look at this here, I kind of find a shortcut. As you know, I introduce here now George knows Bob, and Bob knows Ted, and Ted knows Lisa. So rather than going all over the place, which is the longest way, now we have a shortest path. And if I run this now, George knows Bob, Bob knows Ted, and Ted knows Lisa. So my shortest path, as you can see, worked here, and find what, whenever I introduce new relations, I was able to actually find the shortest path. As I said before, you can use other columns, as in this one. Forget a comma here. And you can use all kind of aggregated functions that I counted out there. As you can see, there are 3 hops to find Lisa and from the George. All right, that was the shortest path. Now, what else we can do? Graph database tables can work with any other really data types. So that makes them really interesting whenever you are creating data models. Whenever you are looking for, if you want to create like smart data models without using, all that R, Python, or data science things, actually you can use the graph database for that. For example, what I'm going to do here is, let's say we have an e-commerce website, and we are a pretty large company. We have many warehouses, and users goes and orders products, and let's say we give them free shipping, right? Now it's free shipping for them, but somebody has to pay for it, so we are paying for it. So we really need to be careful, since we have many warehouses. So if a user actually buys a product, we want to choose to send him from wherever is the closest warehouse, right? And we want to create some kind of like a smart application, which is going to pick the right, I guess, warehouse, depending where the user is. So I'm going to try to fix that problem in here. So what I'm doing here is, first, I have my products table. Products table is an entity table. I have my warehouse table, which is I'm gonna list all my warehouses. And I'm going to have my users. Those are going to be my users information. So those are going to be my node tables. The important thing here is, as I say before, you can create any kind of data type in graph database tables. So as you can see, I am creating geospatial data type in warehouse. This one actually pinpoints where my warehouse is. I know exactly warehouses, so I can get my latitude and longitude of the warehouse and put it right here. Also, I have the same thing for users. Now, finding the latitude and longitude of your user is not going to be that easy. Not everybody's going to actually share that with you. But guess what? You don't need the latitude and longitude of your user. If you know which city they live, which you should have that already because they give you the address anyway, you don't need to know exactly where the user actually is. Yeah, you are right for shipping, you are going to know exactly. But if you're going to try to find the latitude and longitude of each user, which you can do it, but probably that's going to cost you money. And in my case, I really don't care. I don't need to pinpoint my user. As long as I know which city or maybe zip they live in, I should be able to get like an estimate, like how much this will cost me to send the product to them. So in that case, all I'm doing here is I'm just getting the city location. Then I have a relation table in stock. This is going to actually happen only when a user buys a, actually this is going to happen only whenever a warehouse has the product. So this is gonna be between the product and warehouse. The other one is the in process, and this is gonna happen whenever a user buys a product. This is gonna be the relation. So let's actually create these structures first. Now we have our tables. We are happy. Now we need some data. For data, what I'm gonna do here is I'm gonna put bunch of products in my product table. As you can see, so there's nothing different here. I'm just using the insert statement. Then I'm going to add my users. So I don't know how much experience you have with the geospatial data, but you have to use the geography for this. And I'm creating a point. Those are the latitude and longitude of the city they live in. And this is the Kansas City, Memphis, Cleveland. So those are really, you can find them for free from anywhere. This is a public information. So I'm just getting all this information and putting them in my table, users table. Then I need my warehouses. I say I'm a large company, and I say I have many warehouses in those different locations. Also, I know exactly where my warehouse is, so I'm just passing their latitude and longitude here. Now, let's actually run those. These are my node tables, entities. So let's run this. Now I have a bunch of data here. All right, now, next, we need to create some relations. The first thing I'm doing here is in stock relation. So I have a warehouse, and I'm just saying that this warehouse has this product. This warehouse is this product. So those are the relations I'm creating. And this is going to be for in stock. So let's create all these in stock relations here. Let's do that. The next one is going to be in process. And this is going to be between user and product. Whenever a user buys something, we are going to create this relation between the entities. And I'm just passing the get date here because I want to track when actually this happened, when they buy it. So I can actually keep that in my in process relation table. All right, so let's continue here and create all these relations. Now we have all the data. We are ready to query the data. So as I said before, I'm going to use some geospatial data. What I'm going to do here is I have an inner query here, which I want to run first. What I'm really doing here is, if you look at my match first, I am actually going from my users table to products table, and I'm finding all the products they buy. Look at my direction, I'm going this way. And also I'm using actually another direction. I'm saying that I want to find all those products from the warehouses I have. So if I have that in multiple warehouses, I want to see them. Also, I'm using some geospatial data functions here. Yes, the distance will actually give you the shortest distance between two locations. In here, I am actually finding the locations. I'm finding the distance between the user and my warehouse. So if I run that, this is going to actually give me all the products in process and all the warehouses I have. If I run that, as you can see, it looks like George. He's from Virginia City. He is buying a 27-inch monitor. And it looks like I have this 27-inch monitor in 3 warehouses. I have in Minnesota, Dallas, and Seattle. Now, if you look at this is actually telling me what is the distance between this user and my warehouse. And it looks like if I actually send this 27-inch monitor from Minnesota, it looks like it's going to be probably much cheaper for me to send this. And as you can see, you can find all other in process, and really you can make the decision here and try to figure out where should I send this product from. To do that, I'm using a window function here, the rank over, and as you can see, I am ordering by the miles, and the first one is gonna be the one always the shortest between user and my warehouse. As you can see, this is the shortest. George, Virginia Beach, Mike, Las Vegas is 605, and Tom from Cleveland. Actually, there's only option 1 here. So you can really analyze this data easily. So as you can see, I'm going to say here, just give me the priority 1, which is going to be the shortest path. So if I run that, it's going to actually give you not everything, but only what really matters. So those are the things that I need to send to these users from these warehouses, because they are the closest one. And it's going to be cheaper for me. Also, you can use this to analyze your data. So if you actually look at that, and if you find some interesting things, maybe a lot of people, for example, buying this product, and maybe they are not 1,200, still pretty large, a long distance, and it might cost us a good amount of money. Maybe we need to make this 27-inch monitor available closer to, close to Virginia Beach. Maybe we have a lot of users out there. Maybe we can actually save money by doing this. So as you can see, I didn't really use any kind of R, any Python, any kind of machine learning here. All I did is I used a SQL Server, and I was able to combine some of the, good data types. I used the geospatial data and graph database tables. I was able to dynamically create the relations between the entities. And I have a smart data model here and I can depend on, which is great. All right, so I'm going to actually show you one more demo, because the first thing I really hear is from people like, okay, node tables and edge tables are great, but they are new and we don't know how well they're going to do when you have a lot of data. So I don't know what a lot of data can be. But in here, really, yeah, this is great. But how much data I have? Of course, it's going to be fast, right? Which I hear that sometimes. So I say, okay, what if I actually push a lot of data in this? So I have one example here. What I did here is I had the Stack Overflow, and I actually create the graph data model for the Stack Overflow data set. And okay, this is not really, I guess, not that big, but it's much bigger than what I have been showing to you. So let's actually pick the, I guess, right connection here. So let's change the connection. All right, so what I did here is, really, I'm not gonna go very complex, but I have my users. and each user can ask question in Stack Overflow. So I have my questions here, right? And as you can see, there are some not good, I guess, data types here that we are not fan of, but they are still here. And after question, each question can be answered, right? And this is the relation table. It's between the user and question. The user asks question. And I have my answers table, which answers can be, well, answered. So we have a answered relation, as you can see. Now, I'm not going to go in all those. This all it does is it just goes to Stack Overflow dataset and start to create those relations. So I'm not going to actually go into that. But I want to actually show you when I have the data, how fast these queries are going to be. So let's actually look at how much data we have. All right. Let's use the right data tables and database. Now, as you can see, yeah, it's not maybe, I guess, that big data, but it's much bigger than 5, 10, or 20, rows we just created. So looks like we have in questions, we have 1 million rows. In answers, we have 2.5 million, and we have a good amount of relations between them. So we have a good amount of data here. Now, if I'm going to actually go here, and for example, here, what I'm doing here is I'm going from my users table to question table by using the ask relation. This is going to give me all the questions asked by this user. So if I run that, pretty fast, 0 seconds, 15 rows. And I should be, I think I did this good. So this should be hitting the indexes too. See? Yep, cluster index. So everything is working fast. So this is pretty simple though. What else we can do here is, what I'm doing here is I can make it more complex. As you can see, I'm hitting more tables here. And what I'm doing here is I am going from user table to question table. I'm still finding all the ask question by this user ID. I'm saying and I'm not stopping there. I am looking only question ID 11. What answers actually was answered. So if I go here, this is gonna give me this all questions actually asked by this question by the name. Those are the answers, and those are the answer text for question ID 11. Still, not even 1 second. And this is great. So, I use node tables and edge tables. And yes, I don't really have a very large data set for it. But as you can see here, 1 million, 2 million, 5 million, it really didn't make sense. And that's my personal computer. It's not really like a server computer. And I get good results. So I'm happy with graph database tables in SQL Server. And if you will have, any kind of questions about it, what I show you here, please, you can ask me after the session or from my contact information. All right, so that's all I have for you today, and I hope everybody learned something new today. I was very happy to give you this session. As I said before, you can follow me from any of those social media. Check out my blog, and thank you again for joining me today.